this lecture, we will address load paths and look at some examples of loads and load paths in airframes. First of all, I want you to understand the concept of a load path. The load path is a physical trajectory that links the location of the applied force and forces elsewhere that provide equilibrium with the applied force. This trajectory should be able to carry and transfer the loads. Let's look at an example. We see a point force acting at a certain location in space, and we want to connect it to the wall with a structure that is in equilibrium. If we look at the case where the force is applied downwards, there are several solutions to create equilibrium. A simple cable or rod would be sufficient to create the load path, and the cable would be loaded in tension. If we look at the same situation but with a force which is applied horizontally, the cable will not be sufficient because a point force would cause the cable to rotate, and the structure would therefore not be in equilibrium. Hence, a load path that can resist bending is necessary for this structure, for instance by a beam. Now we're going to take a closer look at that beam and the influence of the cross-section of that beam on the loads and the stresses in the beam. Let's consider a simple structure, a clamped beam on which a vertical downward load is applied at the free end. This load will cause a deflection of the beam. This will create tensile normal loads at the upper surface, compressive normal loads at the lower surface, and shear loads in the webs. If we then take a look at the different cross-sections of the beam, we can see that in case A, the I-beam, and in case C, a solid cube, the applied force is aligned with the center of the cross-section, and hence with the shear forces acting in the web. For case B, however, the shear forces of the beam are not aligned with the applied force. Because the shear web is located at a certain distance from the applied load, an extra moment on the structure is created, in this case a torsional moment. And it makes the beam rotate on top of the vertical deflection caused by the applied force. Now we will further investigate the I-beam and the loads and stresses it carries due to the vertical force. We first look at the side view of the beam, take the flanges and the web apart in the figure to assess internal loads, and apply the vertical load. The upper flange is in tension, the lower flange is in compression, and the web is loaded in shear. These are the load paths within the structure. For the structure to be in equilibrium, the applied force F times the length of the beam needs to be equal to the normal forces times the height h. How does that translate into the normal loads in the beam? At the free end of the beam, the normal forces, tension and compression, will be zero, and they will linearly build up towards the root. If we cut a section of the beam at whichever location of the beam, the equilibrium will always be provided by the increase in normal forces and the shear forces that the web applies to the flanges. We now know the normal forces increase towards the root of the beam. What about the shear forces? If we cut a section of the shear web away, what would happen to our normal forces? Nothing. They are not increasing in the area where the web plate is removed. The web plate provides the equilibrium vertical force component. Now we've seen some simple structures and loading. Can we now apply this knowledge to actual airframes? The lift generated by the wings will cause the wings to bend upwards, similarly to the case of the clamp beam we've just seen, while the weight of the fuselage will cause the fuselage to bend downwards. These lift and the weight forces are considered as distributed forces. There are also examples of concentrated loads, for instance the forces applied by the landing gears. Consider an aircraft on the runway. The forces acting on the landing gears are in equilibrium with the total weight of the aircraft. If we look at a vertical tail subjected to a wind force on an airplane standing still, we can represent it with a clamp beam in bending under a distributed load. The wind force is in equilibrium with the forces at the root of the vertical tail. But this is only the part of the vertical tail. If we now consider the whole structure and assume that the fuselage is clamped at the location of the wing, what we can then see is that the bending moment on the vertical tail will rotate the fuselage. This will cause the fuselage skin panels to deform in shear. You thus have to consider the whole load path in the entire airframe and consider all the loads. What we have seen today is that when we apply external loads, our structure, the load path, will deform. This deformation will create stresses, compression, tension, and shear stresses.